Hello, this is an AQA revision video for statistics, or S1. Topic today was Pmcc, also known as product moment correlation coefficient. Okay, product moment correlation coefficient is a measurement or measures the degree of scatter. So you may have already come across regression. Product moment correlation coefficient is how good or how accurate that regression line is.
The Pmcc tells us how strong correlation is. So you've done correlation before in GCSE. Pmcc is how we can tell how strong the correlation is.
And it's the correlation between two variables. This is also known as bivariate data.
And it uses the mean and standard deviation of each variable. Now the Pmcc takes values between 1, positive 1, and negative 1. With positive 1 being perfect positive correlation and negative 1 being perfect negative correlation. In between you have 0, which is no correlation. And as you get closer to 1 or minus 1, the correlation is stronger, and closer to 0, it's weaker.
You cannot have a correlation greater than 1 or less than minus 1.
So here are a few scatter diagrams showing correlation. If you look at the left-hand side, we've got 1, which is perfect positive correlation. If you look at all the points, they are actually exactly on a straight line. So as we go toward the right, the correlation is getting weaker. We've got 0.8, 0.4. They are both positive, but they're weaker. And at 0, you have no correlation. As you see, as you go from 1 to 0, the points are dispersing more. They're more spread apart.
There's no pattern.
There's no pattern. And then as you go from 0, as you carry on going towards the right, we've got minus 0.4, minus 0.8, and minus 1. Our correlation is getting stronger, but in a negative sense. And at minus 1, we have perfect negative correlation. Again, the points are all on a straight line.
Okay, look at this next chart, so we can see all or most of these have a correlation of 1. Or minus 1. The reason why these correlations are of 1 is because they are all in a straight line. All of them are matching up, they're all perfect correlations. As you can see, the gradient doesn't matter, the steepness does not matter. What makes it the positive correlation, or makes it, the perfect correlation, the correlation of 1 or negative 1, is the fact it's in a straight line. In the middle, we can see quite a strange and unusual correlation.
Yeah, so in the middle, it actually goes back to the definition of Pmcc, and we will actually look at one of the formulas for Pmcc, where you're dividing by changes in y. In this case, as we go from left to right in this single diagram, the y isn't changing, so you'd be dividing by 0, and that's why the Pmcc is undefined.
Okay, now looking at these final graphics, we can see the correlation for all of these is 0. Reason being, however, they do have a pattern within them. However, the key is the Pmcc only picks up linear relationships. The relationships exist, but they're not linear, hence Pmcc is giving an accurate reading or a reading of 0. This would also be the same if there were two relationships. For example, even if they were perfect, Pmcc would not pick up a dual relationship or two relationships within a single set of data, and this is one of the reasons why scatter diagrams are so important with Pmcc. A scatter diagram prior to calculating Pmcc demonstrates there is either one linear relationship that can be calculated. So Pmcc interpretation, what we have here is a scatter diagram with assessment scores up the left-hand side, and across the bottom, classes missed per term. Now, in this question, we're being asked to estimate without calculations. We'll do some calculations later, but right now, without calculations, the product moment correlation coefficient between these two variables, A and C. Now, how are we going to do this?
So when you're doing a question like this, we can just estimate the Pmcc just by looking at the data. So I can straight away say it's going to be negative correlation. But a more reliable way of getting a good estimate for your Pmcc is to draw 4 quadrants, or rather draw quadrants. So to do this, draw a box around your data, so have horizontal lines at the top and bottom of your data, and 1 in the middle, and have vertical lines again at your minimum x value, 1 at around your maximum x value, and 1 in the middle. So now if we look at the data here, I've got 4 in the bottom right corner, 2, or almost 3 in the top left corner, and 1 all the way over here in the top right corner. So I definitely know it's a negative correlation. I'd go so far as to say it's strong negative correlation. So an estimate I'd use was maybe minus 0. So Pmcc would be around minus 0.7.
Okay, excellent. I think the key thing here is to remember this is without calculations. What's been drawn here is not considered calculations. However, had you done calculations, you would be losing marks. Also, as well as having Pmcc equals minus 0.7, you could also use the value R is also equal to minus 0.7. It means exactly the same thing. Second part of the question asks to interpret the correlation. Now, for this, we need to consider key things. We need to say this is going to be a negative correlation. We're also saying this is minus 0.7, so we're going to say a negative strong or a
strong negative,
better English,
Thank
strong negative correlation. Correlation is the key words here. We also need to say, reference what these two variables are on the axes. So it's a strong negative correlation between the assessment scores and the classes missed. Now, in layman's terms, what does that mean?
The more classes you miss, the worse you'll do.
However, hopefully by watching this video afterwards, that will help you in terms of your revision. But you shouldn't miss classes. Now, our estimate previously was minus 0.7. It turns out, reading the data, the actual answer is minus 0.75. Because this is an estimate, this would still be seen as the correct answer. In fact, anything from minus 0.6, which would be the bottom end of a strong negative correlation, to minus 0.9 would be accepted here. Now for this next question, we're told that one of the values circled is now removed, and we then have to estimate the new product moment correlation coefficient.
Now if we look at this value over here, the value that's circled, it's quite far away from the rest of our data. The rest of the data is quite tightly packed around a straight line, but this one is quite far away. So we can see this piece of data as an outlier. Now if we remove this piece of data, the rest of our data is even more strongly correlated than all the data put together. So I'd think my correlation will get stronger. So instead of minus 0.75, I think my correlation may be now maybe minus 0.9. Do you agree with me, sir?
Absolutely. For this question here, again, it's an estimation. We don't know exactly what we're looking for, or what the examiner is looking for you, is the fact that with this outlier taken away, this outlier removed, then the data will be more correlated or in a straighter line, hence the correlation increases, and what we have is a minus 0.75 increasing to a minus 0.9, or increasing in terms of correlation. Final question is advised, why is it advised the scatter diagram? We mentioned this slightly before. Why use a scatter diagram before calculating the product moment correlation coefficient?
So the first answer, one possible answer to this question is staring us in the face in the diagram. When we draw a scatter diagram, we notice any possible outliers. We can also notice when drawing a scatter diagram, as we said earlier, any non-linear relationships, which is really important that we notice those, because Pmcc isn't useful when we have non-linear relationships. Rather, it's not only is it not useful, it doesn't apply. We can also notice dual relationships, so non-linear relationships, outliers, and dual relationships, all of which will affect my Pmcc, and in the last two, make my Pmcc useless.
Our next part of the questions that we're looking at is interpreting product moment correlation coefficient, or R. And here we have a template set up. We have the words strong, moderate, weak, almost no. The idea is to select one of those. It's either positive or negative, and then correlation between, and then after that you refer back to the variables listed in the question. So using this as a template, we're going to interpret the following results. The time spent studying and the final examination mark R, which is Pmcc, equals 0.78. So R equals 0.78. So we're going to use the framework above to work out, interpret the following results. The strong correlation is anything for the modulus of R, that means either a positive or negative value of R, to be less than 0.9. Anything bigger than 0.9 you say is very, very strong or almost perfect, very rarely happens, and less than 0.6. Moderate correlation is when it's going to be less than or equal to 0.6 all the way down to 0.4. Weak correlation, less than or equal to 0.4 all the way down to 0.1, and almost no correlation is greater than 0 and less than 0.1. Okay, these are approximates. On the borderlines here, the 0.6, the 0.4, you could either use the moderate or weak, or moderate or strong. However, these are roughly where they should be.
So in this case, R is 0.78, so we would say it's strong correlation. Now, it's positive as well, so we can say strong positive. Finally, the correlation, it's in between time spent studying and final examination mark. So there is a strong positive correlation between time spent studying and final examination mark. On part 2, vegetables eaten daily and doctor appointments have a correlation of minus 0.4. So looking at our template, minus 0.4, you can either say it's moderate or weak. Either is fine. I'm going to say moderate. So I'll say there is a moderate correlation, but it's minus, so it'll be negative. So there's a negative moderate correlation between vegetables eaten and doctor appointments.
The final part, the interpretation, just refer back to the question itself.
Yep. So it's very important you refer to that. If you don't refer to that, you will lose a mark.
Okay, for this next question, we are going to calculate the product moment correlation coefficient, also known as R, from a table of data. Now, this question, the blood pressure, P, and the ages, T, of 7 hospital patients are shown in the table below. Now, we're going to calculate the product moment correlation coefficient using the calculator.
Okay, so get your calculator open, and the first thing we want to go into stat mode. So press mode, then press number 2. It says stat there, press number 2. Now we're in stat mode. So to do Pmcc, we want the second option here. So A plus Bx, so press number 2. So you'll have a table of data here. So if you look at our table of data, we've got T and P, but we've got X and Y here. So when you're doing Pmcc, it doesn't really matter which one you call X, which one you call Y. So T can be X and P can be Y, or the other way around, as long as when you put your data in that you're consistent, so all of our X's will be T's. So in this case, T and P, doesn't matter what we call them, X or Y. Usually you have your explanatory or independent variable as your X, and your response or your dependent variable as your Y. So I'm going to have X's, my X is going to be all my values of T's. To enter 42, I just press 42 and then press equals. Now to enter 74, this is my second X value, I'm going to press 74 and then equals. And you carry on and enter all your X values. So it's 42, 74. Okay, now that I've entered all my X values in, I want to enter all my Y values. So I'm going to use my arrow keys and go to right to the top and press right to go to your Y values, and now enter all your Y values in. So first value is 98, and just press, after you've entered one value in, press equal, and you go down to the next line. So 130 and 135. Now, it's very important when you do this that you go back and check all your values. This is usually a 4-mark question, and you can very easily lose those 4 marks if you typed it in incorrectly. So I'm going to just do that right now. So 60, 135, 20, 80, 20, 26, 80, 56, 182, 35, 88, 48, 120, 74, 130, and 40, to 98, and that's all correct. So once you've got all your data in, press AC, press all clear, and that stores it in our memory. Now to find the Pmcc, you're going to press Shift, and then number 1. If you look above the number 1, it says stats. So Shift, number 1, you see this screen. To find the Pmcc, you're going to go into regression, press number 5, and now Pmcc is your R, so it's number 3. And finally, you need to press equals. And we get a Pmcc of 0.701, so on. We're going to round this to 3 significant figures, so we get a Pmcc of 0.701.
It's very important you have the R equals there, so the examiner knows exactly what you're calculating, or he also knows that you know what you're calculating. Pmcc, the variable R.
Now finally, they ask us to interpret this result.
And this leads back to the questions we've had before. Now, remembering or recalling what we had as our template, we need to think about initially. We have 0.7. 0.7 is strong. It's positive, so it's a strong positive. Now, correlation is a standard word used here. And it's a strong positive correlation between, we go back to our question, blood pressure and age of patients. So the key things there, strong positive correlation between blood pressure and age of patients. Really recommend you go back to the question for that final interpretation.
Okay, so the growth of sunflowers is recorded at various times after planting. This is the table we are given. We need to work out, find R from the data above and interpret your results. Now R means Pmcc, so we need to find the Pmcc of growth and time.
Coming back into our calculators, we load up into start mode, we choose regression, we enter the data, we check the data. Remember, if we're not showing any calculations for this, so we need to make sure our data is correct, because it's going to mean the answer correct or incorrect. Our final answer is R equals 0.745. We round our answer to 3 significant figures. We're also asked to interpret these results. Now, let's think about this. We go bit by bit or part by part. We're looking at the 0.7. 0.7 means it's going to be strong. 0.7 is positive, so it's strong positive correlation. Then we lean back and think about going back to the question. So it's strong positive correlation between the growth of sunflowers over time.
The results of growth were recalculated in feet. We're now given this new table where instead of growth being measured in centimeters, growth is measured in feet. These are the same values or the same plants as the plants over here. We are now asked to calculate a new value for R.
What I'll ask you to do now is pause the video, calculate the value for R, and then we'll go check if you've got it. So pause. Okay, welcome back. Your value for R should have been exactly the same.
0.7. Correct.
We're both correct.
We're both correct. Your value for R should have been 0.745.
Now, the Pmcc, or the value for R, has not changed. The reason being that unlike standard deviation, or unlike the mean, Pmcc remains exactly the same. That means the Pmcc is not influenced by linear scaling.
This means that if we apply any kind of linear transformation to growth or time, or whatever our variables are, the Pmcc will be unaffected. Now, linear transformation means multiplication or addition. So if you multiply one of your variables, your x value, by what number, and then you add another number on top of that, it will not affect your Pmcc. And likewise for your y values. So whatever the two variables are, if you multiply or add them by anything, your Pmcc will be unaffected. So now we're going to calculate Pmcc using the formula. A meteorologist believes that there is a relationship between height above sea level, h meters, and the air temperature, T degrees centigrade. Data is collected at the same time from 9 different places on the same mountain. And we're given these 3 different values, SHH, STT, and STH. Now, first thing we need to calculate the product moment correlation coefficient from these 3 values.
Okay, the product moment correlation coefficient is also equal to R. Now, the formula we need for this is ST of H divided by the square root of SHH multiplied by STT. This is the alternate method to calculating product moment correlation coefficient. You must also be fluid with this as well. So in terms of calculations, we substitute the values in. STH divided by the square root of SHH .58575. Rounding it to 3 significant figures, our final answer would be 0.586 to 3SF. A little check to it, a note to ourselves, this is a value that's in between +1 and -1, so it's the right sort of value you would expect for the product moment correlation coefficient, or R.
Yep. So, as looking at this question, we have SHH, STT, STH. Of course, your variables won't always be T and H. You'll have X and Y's, or they could be anything. They could be using any letter depending on what the question is. Always remember the normal form of this formula will be S XY over the square root of SYY SXX. An easy way of remembering is just remember the one that's different, where the 2 variables are different, so SXY, or in our example STH, is the numerator, and the denominator is the square root of the 2 things, is the square root of the product of 2 things that are SYY, XXX, or in the other one SHH, STT. Then you've got doubles there.
The second part of this question mentions a miscalculation of measurements, which the height was 10 times greater. Now it asks us to comment on the Pmcc results.
So if I understood the previous slide, as Pmcc is not affected by linear transformations or linear scaling, the Pmcc should be exactly the same, so 0.586. Done. Uses?
Okay, we have some interpretation questions we're going to whip through and looking at Pmcc. The first question. We have a scatter diagram, we have variables A and B. The Pmcc for this data is minus 0.7. Minus because it's going from the bottom right up the top left. Now, the piece of data circled is removed and we're asked to find out, or this outlier is removed and we're asked to find out what the Pmcc is. So we have a value of minus 0.7 and what would the new value be?
So the Pmcc will now be, the outlier has been removed, so in magnitude, my Pmcc will be more. Or you could think that my correlation will be stronger. It's still going to be negative, so it's going to be stronger negative, so it's going to be closer to -1, so I'm going to estimate minus 0.8.
And in fact, any value between minus 0.7 and minus 0.99 would be accepted. 1 minus 1 would not be accepted because it's not perfect correlation, but it's to show you anything there would be. So in this next question, we're estimating the product moment correlation coefficient, or R, without any calculations. It's very important we don't do any calculations here because the question specifically tells us not to. Now to do this, we need to find the largest and the smallest data, or piece of data, in terms of the X, we bracket that off, and also in terms of the vertical axis, which is known to be Y, we also do the same. Now, finding the median of both of those 2 values gives us 4 boxes or 4 quadrants that surrounds the data. And within that, we can see the majority of the data is in the top left or the bottom right. In fact, 8 of the points are in the top left or bottom right, which tells us it's a negative correlation. And we can say the estimated value, because 8 of 11 minus 0.4 to minus 0.6. So if we were interpreting this, would say there'd be a negative, a moderate negative correlation.
Now, a few points are now removed. So these 3 points are removed. What would you estimate the correlation to be now?
Now, because all the points now, there are less points, there are 8 points, and they're all either in the top left or bottom right, we'd now say the correlation, the magnitude, it's still negative, but the magnitude's increased. So anything we can say from minus 0.7 to minus 0.8.
So now what we want to do, we want to change the correlation. We want to do something so our correlation is even more negative. So our correlation is closer to -1, or in other words, it's less than minus 0.8. So what do we need to do there?
But at the moment, all the data is either in the bottom right or the top left. So to increase, so at the moment, they're in the right quadrants. But to have a greater correlation, what we then need to do is have it in closer to the regression line or the line of best fit. So these points would have to move closer to the line. If they were perfectly within the line, then we'd say that was a perfect negative correlation, which would be -1, but they certainly need to be closer if it has a greater magnitude than minus 0.8.
Alternatively, another way we can make our correlation stronger and more negative is by adding points closer, or adding points around our line of best fit. So if we weren't moving the point, if we weren't allowed to move the points, so we can't change our data, but we are allowed to add new data. If we added data around our line of best fit, you can now see our data is now even more strongly correlated in a negative sense, so our value will be less than minus 0.8.
Okay, our final questions are looking at interpreting the validity of some Pmcc results. So we're really looking to see, this is the data, we're interpreting it, is there any misconceptions or is there anything, errors within this data? So we're going to comment on the results of the following variables. First of all, nose length and ear length has a Pmcc or R value of 1.2.
Now, if I remember correctly, we said that our Pmcc, our R, takes values in between and including 1, positive 1, and negative 1. So how can we have a Pmcc of 1.2?
We can't. So it must have been, it's an impossible value. The R cannot be greater, or the modulus of R, or magnitude of R cannot be greater than 1. So here we have a miscalculation or an error within the calculation of the data. The second question asks for the arm and leg length to be minus 0.8.
Now, minus 0.8 is a possible value for R, but it's unlikely that there's a negative correlation between arm length and leg length. I imagine as someone gets taller, as someone's arms are longer, their legs will probably be longer as well. So while R value of minus 0.8 is possible, it's unlikely.
Exactly. Our final set of data talks about height, or states that height and weight has a perfect correlation of positive 1.
Now, height and weight, I imagine, does have a positive correlation. As someone gets taller, I do imagine they will, in general, normally weigh more. So we would expect to see a positive correlation. But we know that that's not always the case. There are outliers. There are people who are tall who don't weigh very much, and there are people who aren't very tall who weigh loads. So it's very, very unlikely that you'll get a Pmcc of 1. A perfect correlation is very unlikely.
Estimating Pmcc without calculations, we have 2 graphs, and the question being asked here is which set of data has the greatest value for R? I want to justify that answer.
Now, looking at these 2 graphs, I'd say the right-hand graph has a bigger value for R.
Why?
Now, I'd say the right-hand graph is, if you look at the points, they are closer to the line of best fit. So it has stronger value for R.
But the graph on the left-hand side has a steeper gradient.
Yeah, but gradient, the only thing that gradient tells us is if the correlation, or if R is positive or negative. Once, in this case, both graphs have a positive correlation. After that, the gradient doesn't tell us anything. Pmcc is all about how close the points are to a line of best fit. So clearly, the graph on the right has points closer to the line of best fit.
So the graph on the right hand side has the greatest value for the magnitude of R.
Now we're going to be interpreting some values for R again.
So a quick recap.
We had a template for interpreting. We had either it was strong, positive, either it was strong, moderate, weak, or no, and then we had positive or negative, and finally we had to describe, or we had to relate it to our data.
Okay, so looking at this first question, it has a R value of positive and it's 0.35. So we'd say that was a weak positive correlation between the age of the spaniel and the tongue length.
Now number 2, the number of takeaways consumed each month, and BMI, which is body mass index, has a value for R of 0.69.
Again, this is positive. It has a value of 0.69, so we'd say it's a strong positive correlation. Those are the 3 key words. And follow that up in terms of referring back to the question. So it's a strong positive correlation between the number of takeaways consumed and the BMI index. The final question, the hours a student spend procrastinating and percentage scores in their examinations.
Now, R has a value of minus 0.9, so it's minus, so it's negative. It's 0.9, so that's a strong correlation, so it's got negative, strong correlation, and it's between the hours students spend procrastinating and the percentage score in their exams.
I.e., the longer a student spends procrastinating, the lower scores they get in their exams.